Can everyone see my screen? Hello?
Yeah, you're audible.
Okay. So I want to do this. Let me see. I think yesterday, I think we left here about the renewable power. So how to integrate the renewable power into the green ammonia production. So this picture shows the windmill on land and the windmill in the ocean. Okay. So I sent email to Dr. Anand. I'm trying to do a quick survey here. Yeah, I tried to do because this is online. I could not see your response in the classroom in person. So I want to do a quick survey. So I was told in the audience there are two different type of the students, chemistry, chemical engineering major. The other students are the maybe industrial engineering. So I would like to do a quick survey to understand from yesterday. What do you think the level of details of my lecture? Do you think the speed too fast or too slow? So, for example, if you are chemistry or chemical engineering major, what do you think? Do you understand what I'm lecturing, or it's too simple for you? You want deeper, or if you are not a chemistry, chemical engineering, so what do you think? Do you think, oh, this is too detailed? I don't understand. So for the moderator, can you select the two students? One student is in chemistry, chemical engineering. Just speak up, tell me. The other student will be other majors. Can you do that? I want to hear. I want to do a quick survey. Please do that. Yeah. So first, is there in the audience? Is there any the chemistry, chemical engineering student? Can you say something?
Chemical engineering, company, one, only one. Chemistry, engineering, one chemistry. One person from chemistry, sir.
One from chemistry. Can you have that student tell me if that student understand what I'm like, the nature or the content of my lecture yesterday? Can you give the microphone to that student?
Yesterday,
yeah, I still able to understand. In chemistry point of view, I can understand.
So you understand it, all right? I cannot hear you because there's some the noisy behind the audio.
In chemistry point of view, yesterday lecture I can understand. As a chemistry student, I can understand.
Okay, so you understand. Okay, so you understand the principle. So can you pick? So that means there's only one chemistry student because yesterday, from yesterday lecture and also the questions, I have a feeling that not many students are in chemistry, chemical engineering. That's why I slowed down quite a bit. So I couldn't finish my lecture yesterday. So that's why I need to continue today because if I speak too fast or if I skip a lot of the very basic theory, I think some students may not understand. So let's do that. Looks like only one chemistry student, others are not chemistry. Can you give the microphone to just any student whose major is not chemistry, not chemical engineering? I want that student to tell me if he understands. Just give any student. Speak slowly. Just tell me, yeah. Mechanical engineering. So if you major in mechanical engineering, yesterday you were in the class. Do you understand the content of my lecture yesterday? You understand, correct? Is answer yes? You answer.
100%, I can understand your lecture very clearly and loudly.
Okay, so let me repeat. Okay, I'll do this. I have to write something. I cannot hear the background noise. Okay. Oh, hold on. Sorry. Okay. Sorry, I typed something wrong. Because I cannot hear what you're saying. So I'm typing in my question. From mechanical engineering student, you can understand my lecture yesterday, correct? I just want to know yes or no, correct?
We can understand it clearly, sir, because we have studied the thermodynamics and also we have studied little chemistry about Haber washers and also we understand your yesterday introduction very well, sir.
Thank you. All right. So now I'm typing next one. I'm going to it looks like my audio is clear, so you can understand. The problem is when you use a microphone to speak, I could not hear clearly from you. The reason being that there are a lot of the echo in the behind. That's why I'm typing the question. I'm going to continue the same speed. Just read my question, okay? I'm going to continue the same speed as yesterday, as I did.
Sir, could you hear us now?
Hold on, I'm wait until I finish, okay? As I did. Okay, so I'm going to continue the same speed as I did yesterday. Would that be okay? Just say yes or no. That's all I can hear.
Yes, sir.
Say yes or no.
Yes, sir.
Okay, thank you. All right, so that's exactly what I'm gonna do. All right, so that's why I say that it's very difficult to teach online without getting the feedback as in the classroom, but I'm trying. So that's why I frequently stop and asking questions, try to understand if you understand my lecture, okay? All right, so let's continue yesterday. So sometimes I put in the presentation mode, sometimes I put into this mode because I can type in my question so you can answer, okay? So, all right, so we talked about the using renewable power to make ammonia yesterday.
That is better.
Did anybody say anything? Any question?
No, sir, could you speak if possible?
All right, so no question, okay. From yesterday, we use renewable power. When you use renewable power, essentially you use water as a feedstock. You have renewable power, you do electrolysis, you get hydrogen. There's no carbon involved. So basically, that's why we call it green ammonia. Green ammonia means there's no CO2 emission. You follow me? So that's whole discussion yesterday, the second lecture. So now keep in mind, biomass also is renewable feedstock. It's different from the solar and different from wind, but it's also renewable. So what are the biomass? So let me back up. From biomass, you can make a hydrogen. You see my where's my apple? All right. So let's take a look at the biomass. Biomass, the forest, the wood residue. So in the area where I live, it's in Morgantown, West Virginia. There is in mountain area. In mountain area, you have a lot of the forest wood residue. I'm pretty sure if you would go into the somewhere in India, I think northern part of India, there are a lot of mountains. Those trees, they are they could be feedstock of the as a biomass. And another unique situation in the United States is called agricultural residue. From the picture in the middle, these are the so-called cornfield. Okay, so I'm going to write it down. You can see my writing now, cornfield. So it's from cornfield, the residue called store. I don't think you will see so many cornfields in India, only in the United States, because the land is so flat and the soil, so they grow a lot of corn. So those corn today actually 70% into ethanol, and not being fuel. Okay, so based on this chemistry, you basically from the biomass, you can make the hydrogen and CO2. Of course, once you have a hydrogen, you can make ammonia. You see the chemistry in the future. That's why I did a survey at the beginning. I want to make sure you have some knowledge on the chemistry. So this is a different way to make the hydrogen. Once you have hydrogen, you can make ammonia. But keep in mind, when you use the biomass, you do produce CO2. This is different from the renewable power. From renewable power, you do not produce CO2. Renewable power, when you produce hydrogen, essentially you make hydrogen plus oxygen. Is that right? So no CO2. So there's different type of biomass, forest, and agriculture. There's another type of the biomass. It's called the energy crops, and then some people call that the switchgrass. Switchgrass means they grow very fast. They can grow full season in a year. So this is another way to look at the switchgrass. On the last category on the bottom is called the municipal solid waste. It's called MSW. It's called the municipal solid waste. They are also considered as a biomass because every day you generate those waste. So you basically turn that into the hydrogen. Okay. So I'm going to ask a very quick question. So please give that to the microphone to the student who answer. What do you have the biomass in India? So in US, we have 3 different types of biomass: forest residue, agricultural residue, for example, corn store, and the other is the artificial made a biomass. It's called the energy crops. That means switchgrass. Can any students, based on your knowledge, tell the audience what kind of biomass you may have in India? Just raise your hand and use the microphone, please.
We have residues in which corn on the wheat stocks, then rice stocks, cotton stocks, then we have also jute stocks.
Oh, thank you.
Agriculture stocks, and also we have plenty of forest. So there is also forest residue. Similarly, we don't know about that energy grass, that is switchgrass. But
thank you.
Municipal solid waste also, we have plenty of municipal solid waste.
Yeah, thank you. I would like to everyone when you speak, just like this student, speak slowly, clearly. I can fully understand this student speak. So I forgot one thing. Actually, India is one of the largest exporter of the cotton, all right? So the residue from the cotton, basically you take a cotton, whatever leaves left over, those are very good biomass. Okay, so all this can be made into hydrogen, make ammonia. It's called green ammonia. But look at the chemistry. I'm going to repeat. When you have biomass, make hydrogen, and then you produce CO2. Then you take hydrogen, you make ammonia. Why people consider? Think about my question, okay? So I'm writing it down. Let me. So can anybody answer this question? Why people consider? Why do people consider ammonia made from biomass as green ammonia? It produces CO2, is that right? Can anybody answer this question and why the people pushing this way?
Sir, they are like in beside Delhi, there is a Haryana state, sir, Haryana and Punjab. They will grow this wheat and rice paddy crops. So now, once they cut the crop and they will simply firing the waste residues. So that pollution is increasing, and there is sometimes that like vehicles shut down also. Like they are now in Delhi, they are asking the people to run even number one day and odd registration number one day like that. So we can use that biomass and we can reduce that pollution.
Okay, thank you. So basically, thank you. So you have to look at this from life cycle point of view, correct? Anybody understand the life cycle point of view? Life cycle point of view means if you start from biomass, you basically produce CO2. It's okay because the CO2 from biomass, I mean, if you do this for a long time, and then CO2 coming back and grow biomass again, so they go through like a quick cycle. However, if you just start from the coal or the fossil fuel, coal and fossil fuel takes a million years to form underground. Is that right? So that means this life cycle will not start it. So if we use the biomass as a feedstock, this is the cycle. It's called the life cycle point of view. CO2 coming to biomass and you continue on. So basically you shut down the fossil fuel. So you have to look at it from the cycle point of view. So I think that's what your answer is, all right? So this is really life cycle. So that means if I pose another question, you will understand this answer, okay? A plant from produce ammonia, let's say the 1,000 ton per day ammonia using natural gas as feedstock. Another plant of 1,000 ton per day, same using ammonia. Okay. Using Can anybody from the audience answer this question? So a plant produces 1,000 ton per day ammonia using natural gas as feedstock. Remember natural gas, you do steam reforming, you produce CO2, but you produce hydrogen, hydrogen produce ammonia. Same with biomass. If you have biomass, you go through gasification, produce hydrogen and CO2, and then you produce ammonia. Now my question is, same productivity plant produce the same amount of ammonia using the different feedstock. Which plant emit more CO2?
Biomass-based ammonia plant emits more CO2 than methane-based plant.
Yeah.
Because carbon content of methane is 1 for 4 carbon. For biomass, carbon content is higher. One carbon contains 4 hydrogen in methane. For biomass, 1 carbon is have less hydrogen. We need hydrogen. So from biomass, we can harvest less amount of hydrogen equated with carbon means. So biomass will emit more CO2 compared to methane.
Yes, thank you. Very good answer. So basically, I think that if you hear this student answer, so the objective here, I'm going to tell you which plant emit the more CO2. The answer is biomass plant. Okay, so we already talk about so why is still pushing the biomass? Well, because of the biomass you have to look at it from life cycle point of view. So if we do this the continuously biomass hydrogen, then the cycle will start it. So then that means you will shut down the fossil cycle. Fossil fuel takes a million years. Biomass only take the day and the month, right? Because they grow very fast. But the answer is biomass give almost CO2, but in the long run, from life cycle point of view, you still want the biomass. Okay, that's a good answer. Now, I really like this student, how he answered this question. Keep in mind, from natural gas and also from the biomass, you want to produce hydrogen. So which one give you most carbon? You need to look at the two properties. Okay, I'm going to interpret to you. So methane, 75% of carbon, 25% hydrogen, correct? Did you see the composition of methane and biomass? So methane has 75% carbon, but a lot of hydrogen, 25% hydrogen. So biomass has 30% oxygen, which is a problem, and then only 5% hydrogen, but 65% carbon. So you really need to watch the hydrogen content in there and also hydrogen content. So to produce the same amount of the ammonia, so you just watch the hydrogen, your carbon emission will be tied with your hydrogen content, right? So intuitively, you will know to produce the same amount of ammonia, you need the same amount of hydrogen. So from natural gas, you emit less amount of carbon because natural gas has so much hydrogen, all right? But if you use biomass, because biomass hydrogen content is so low, in order to have the same amount of hydrogen competing with the natural gas, you need a lot of biomass. But don't get me wrong, biomass plant emit more CO2. But if you look at it from a life cycle point of view, I think it's considered as a green ammonia. Any question? You understand what I'm saying, all right? You have to look at the chemistry and also look at the how you make ammonia. Anybody has any question? No? Okay. So so basically the biomass is different from as a renewable energy sources is different from the solar and the wind. Oh, I think I saw someone post a question, which is good. Okay. Yes, sir. Okay. So yeah. So basically the someone posed a question is very good. I mean, I really like the feedback from the student. Otherwise, I will keep on talking. Okay, so now I continue the integration of renewable power with the ammonia. So I don't know how many hydropower in hydraulic power in India, but in US in the old days, I would say maybe 1930s or 1920s, they built up so many reservoirs, so many the hydraulic power. You can you are talking about the Hoover Dam in if you ever come to US, you will see that's really good engineering. The hydropower in Alaska, there are a lot of hydropower. So hydropower is very similar to the solar and wind, and then it doesn't need the generator doesn't need any emit any carbon. So it's basically you elevate the water, and then when water flow down, they basically they turn on the turbine and generate electricity. So I'm not going through the technology, and then you have this hydropower going in there. So when the government or the industry build the hydraulic power, they need to have the power grid to the transmission line to the transmit the electricity. That's given. So this is the problem. This is different from the hydraulic power and the solar and the wind. Oh, let me back up. So because hydraulic power takes so much money and also infrastructure, there are a lot of government industrial investment. So when they build this hydraulic power shown here, if you look at it on the right hand side, they already have the investment on the transmission of the grid, to make sure the power generated and distributed nationwide to network. Because there's so much capital investment, they have to have the power transmission and then power generation, they are together. However, solar and the wind, they are different because of investment of the solar and wind are so small. When the industry build the solar and the wind, they don't consider the transmission. Then when I realize, oh, I need a transmission line, it's too late. So in the next couple of the lectures, you will hear how in the United States we solve the so-called stranded renewable power issue. Stranded renewable power means you build power, solar and wind, you cannot put on the grid. You have to solve the problem. Ammonia is the one solution. Okay, so now for the hydraulic power, that's another way to generate the electricity, so-called renewable power. Then the electricity will turn into hydrogen and ammonia. So there's a little bit tricky on the hydraulic power. Have you ever heard of the terminology of the Can everyone read this my notes here? My question here. Renewable power surplus. Ever heard of this?
Yes, sir.
Okay, so just speak up. Just tell me what is your understanding? What's your understanding of the renewable power surplus? Go ahead. Can you speak up? What's the renewable power surplus?
Sir, we usually hear that we have plenty of renewable resources like solar, wind, and even tidal, then hydraulic, in which people majorly in India use hydraulic about 12%, 18%. Similarly, we have other sources like wind also. It is a seasonal. So we used to hear that renewable power is a surplus, but we are not using it. That is the one. I think I have answered your question.
Yeah. Thank you. I hope the audience, the student hear what he said the last sentence. So renewable power surplus, that means you generate the power and then you cannot utilize it, becomes surplus. Is that good? No, it's not good. I will tell you. So why the renewable power surplus? Because you build it up. Let's say for the solar and the wind. So you produce so much solar and wind power, but the transmission line reaching the full capacity. Transmission line, by the way, when you build transmission line, there's a requirement how much power you can put on. Okay, it's not like you can put everything on it. So by the time you cannot put those power on the grid, they become surplus. It's not good. It's bad. The reason being that means the windmill has to spin for nothing. Keep on spinning. When you're spinning, that means you have all of those the mechanical issues, and then basically the life of the windmill decrease. And then when you have a solar panel keep on generating power, electricity without putting on grid, that becomes surplus, but you are still running. But most dangerous things are the hydraulic. When you build a level so high, okay, and then you cannot let the water flow down to regulate the level, what's going to happen? This water dam will be flooded, all right? So that means it will out of control, and then the water will be overflow and then flood the agriculture area, and not what you want. So surplus in the hydraulic is very dangerous. So that means when they see the surplus, unfortunately they have to let water go and generate electricity. That electricity has to be free and let it go. So basically throughout the year they have to generate electricity and then let it wasted, or let the water flowing without turning on the turbine. So there are different ways to handle the surplus. Number one, so in the wind, they basically lock the turbine. Can you believe that? The wind turbine spinning whenever you have a wind, but they have to lock it. Don't let it spin. For the hydraulic, the power, when they have a surplus, that means the electricity they generated cannot be put on the transmission line. You know what they do? They just let it bypass. Sorry, you are wasting hydraulic power. So what's the solution on this? The solution will be every time when you have a surplus of the renewable power, you turn that surplus into the ammonia or any liquid fuel. You can keep or store the liquid fuel adjacent to the renewable power and utilize it later on. That's one of the solutions. So that's why the green ammonia really is very meaningful. It's not just green ammonia. They are hydrogen carrier. They are also the electricity carrier. They can carry electricity and then from place to place, using ammonia. So that's why a lot of the people in the United States, they call the ammonia liquid electricity. It's very difficult to understand why ammonia is a liquid electricity. Now you can tell. So basically, it's energy carrier. Any questions? Yeah, if you have any questions, just use the microphone, okay? So, anybody has any questions? Yeah.
Sir, I have a question, sir, about the renewable power. What you discussed previous. Previously, you said biomass is considered as green power, and then now you are telling hydropower also coming as renewable. Actually, we are not considering biomass as green as well as hydraulic power as a renewable power.
Good question. Okay. So for the hydraulic the power, if you use it's electricity, renewable electricity, you generated hydrogen. So that hydrogen generated doesn't associate with the CO2, all right? So now I like your question. So basically back to the biomass. Biomass doesn't generate CO2. So it's also subject to the debate. So ammonia, I think your question is, you do not consider ammonia from the biomass as the green ammonia. Is that correct?
Yeah.
Because they generate CO2. You have to look at this problem from the life cycle point of view. Life cycle point of view means if you see this, if you do this for 100 years, not today, okay? If you do this for 100 years, they become a healthy cycle. That means You produce the ammonia from biomass, and the biomass grow. Let's say the energy switchgrass, they basically suck in CO2 and keep on growing. So it's different from the fossil fuel. Fossil fuel doesn't absorb those CO2 emitted, but biomass does. So my point is true. If you look at the CO2 emission, biomass doesn't solve the problem on daily basis in the short term. In the long term, lifelong, that's why it's called a life cycle. And then it's called a life cycle. And have you ever heard about LCA? So have you ever heard of the LCA?
Yeah,
It's called a life cycle analysis. And then ammonia is considered as a green ammonia. Ammonia from biomass is considered as green ammonia. I'm not sure. I mean, it's still subject to debate. You can disagree, but if you read the literature or in the general, the public, they consider biomass as a renewable feedstock. So anything from hydrogen from biomass is green hydrogen. Of course, ammonia from the green hydrogen is green ammonia. But don't get me wrong, the process does emit CO2. That's why I posed these two questions. So the question, which plant emit the most CO2? Of course, the biomass emits CO2, but it's still green because you have to look at it from life cycle. Okay, go ahead. You have any different question? Go ahead.
Could you go to the previous slide, sir? Previous slide. Where you mentioned it as a life cycle analysis. Sir, from the point of life cycle analysis, biomass, that is, when you consider the life cycle, we will consider that is the carbon dioxide emission. When the point of biomass, the carbon dioxide emission, that is the plant growth, the raw source, the feedstock, the CO2 emission is very less. Similarly, it consumes CO2, so there is a equivalence in that. Similarly, when we use the biomass as a feedstock, from the life cycle point of view, our carbon dioxide emission is less compared to the life cycle point of coal, because coal, it consumes or it leaves more carbon dioxide when we are producing ammonia or steel. So how do you vary that? How do you clarify with respect to the life cycle point of view for biomass and also for the coal, that is the ammonia production using coal?
Well, a good question. I don't have the word because I'm not expert in the life cycle analysis. I want to go by here. So let me put this way. So I think I'm gonna go by here. I'm gonna add ammonia. Okay, so basically here, the plant. So I think natural gas is not a good example. Okay, so let's do use coal.
Yes.
So the question is, okay, so the question is, which plant emit more? I would say not just CO2. I use the word GHG, greenhouse gas. Okay, I'm changing the question now. So which plant emits more greenhouse gas?
Biomass. Coal?
No, not biomass. This time it's different. It's coal. You know why? Because the coal emits not only CO2, there are other things, NOx, SOx, and all those associated. If you read the literature, NOx, the SOx, you know I'm talking. The greenhouse effect of NOx and SOx. Okay, I saw NOx more than CO2. You follow me? So that's why a lot. I know in India you have no choice. You have to use coal. In US, a lot of coal-fired power plant already shut down. So because the combustion coal or gasification coal emit a lot of GHG, and not just CO2. There's NOx, SOx, and all other pollutants. They cause more greenhouse gas effect. It's more than CO2. You follow me? So my point is, you have to look at. I'm not expert. I don't want to debate on the LCA analysis. So the general public basically think, too, you can still use biomass as a feedstock to produce chemicals, and which is from the greenhouse emission point of view, is better than coal, is better than natural gas, largely because of the oldest of fossil. Natural gas is fossil, coal is fossil, takes a million years to form. That means whatever CO2 you produce will not go back. And then because it takes 1 million years. So it's really life cycle. So I hope the audience has some expert in so-called process simulation, LCA analysis, and you can answer this question. Let me pose question. Any students who's your research associated with the life cycle analysis? Can you tell there's a 3 bullet point? If from your point of view, which one you prefer? From the greenhouse reduction point of view, which process you prefer? Any audience who's a major or the research associated with LCA analysis? So tell me which process you prefer.
I prefer using biomass.
That's exactly the whole world pushing. So based on biomass. So there's really LCA. Anyway, so from previous student question, I still like your question. I like that the student have a different opinion. You're saying, hey, I don't believe this is life cycle analysis. It's okay. So that's why we do research. And then academic research, you basically build the knowledge and you move on, all right? So I can only tell you what the general public believe, because from biomass, I mean, of course, number one, if you have a renewable power, solar and wind, that's a clean cut. You generate hydrogen and then produce ammonia. There's no carbon involved. That's a super clean green ammonia. But in the open public literature, they also see my highlight. They also say ammonia produced from biomass is considered as a green ammonia. It is true. One of the students just a debate saying, no, I don't think that's the green ammonia. So which is okay, but the process does emit CO2. All I can tell you is from general public, even if they emit CO2, but from life cycle point of view, they consider as green. Okay. All right. I think we spent too much time on this to discuss about green or not green, but I think we just move on to the next one. So we talk about the hydropower, right? So keep in mind that there's a renewable power surplus you have to deal with. So from the wind turbine, you have to lock it, and the hydraulic is dangerous because the reason they built hydraulic power 100 years ago, but you don't see it anymore. The reason being that, number one, for electricity generation. Number two, for irrigation. Because when you build it, you can regulate the level and then basically irrigate the agriculture for electricity, and also the agriculture purpose. That's the hydraulic power that they build. However, since the construction of I would say coal-fired power plant or the natural gas power plant, this hydraulic power becomes less desirable because it takes time to build hydraulic power, the power plant, and also that takes them a lot of money, and it takes so much infrastructure to build it. So the coal-fired power plant or even the natural gas combined cycle is so easy to build. So that's why in the United States, you don't see the hydraulic power built anymore. Okay. So in India, maybe the same, but in China, the last 10 years, they still build it for whatever reason. So it's amazing. The cost so much money because you had to immigrate the people in that area. So the surrounding area, you cannot have the people living there. So it's a lot of effort to build hydraulic power. So, all right. So let me move on. So new technological trend to the produce hydrogen. So remember yesterday we mentioned, and this topic continue from yesterday. So you have renewable power, you generate hydrogen. So the easy way to generate hydrogen is so-called electrolysis. Electrolysis, if you learn chemistry, so I'm going to use, where's my, hold on, okay. So basically, if you learn chemistry, so you basically have this. Yeah, positive. I'm talking about electrolysis. This is water, all right? So then you basically connect to the battery, all right? So you do electrolysis. You got hydrogen. That's simple, all right? So yesterday we talked about what's the challenge of electrolyzer. The challenge of electrolyzer is scalability and also the cost, all right, from the cathode. Now, so this is a cartoon really shows from the holder topsoil. If you ever heard of this company, I'm pretty sure they have subsidiary in India. So this is the company called Holder Topsoil. They basically using their solid oxide fuel cell electrolyzer. So solid oxide fuel cell means you have a fuel, let's say natural gas coming in, and you generate electricity. But they run the reverse. Reverse means instead of generating electricity, they put electricity into the cell, they generate hydrogen. So that's a solid oxide fuel cell. I'm going to show you the cartoon. So once you have hydrogen, so this company Holder Topsoil, they basically have all this using their solid oxide fuel cell running reversely. They generate hydrogen, and then they basically build so many applications. So this cartoon I got from their website. If you have time, just read this is SOEC, and it's amazing the scale. We all talk about yesterday about scalability, but looks like the SOEC, instead of scale up continuously, they basically scale out. Scale out means they just multiply. They have a cell, even if it's not at scale, they basically put 100 of them together. So that's a way to scale up. Okay, the different engineer scale up the approach. Engineer scale up, it means you have a small, you build a medium, you build a large. So that's engineer scale up. But there's another scale up, commercialization approach is called scale out. Okay, so scale out means you multiply. Okay, so all right, so this is from the Holder Topsoil. I'm going to, I need to kill my right, what's going on with it? Okay, here we go. I will do this. I will stop sharing, come back. All right, so let's continue to the next one. So why am I? Can you see my slides? Can anyone speak up? See my slides? My slides, my computer freeze. You can see my slides, is that right?
Yes, sir.
Okay. Yeah, somehow okay. Let's move on to next. So we talk about Holder Topsoil. Here's the process. So the Holder Topsoil process. So first they produce green ammonia. So this time is really green because they use their SOEC, solid oxide electrical cell. So it's basically a fuel cell running reversely. So first you have you can have water and then the energy coming in, and then you generate hydrogen, and hydrogen fuel the Haber-Bosch plant. So they use the traditional Haber-Bosch plant. So what I'm going to lecturing in the next couple of lectures from today, tomorrow, and next couple of days is non-Haber-Bosch. Haber-Bosch means high pressure, high temperature. We are talking about the low pressure, low temperature. So it's a different. It still make ammonia, but using different approach. But Holder-Topsoe, the technology is innovation is the way to produce hydrogen is different from the Haber-Bosch, because the Haber-Bosch using the natural gas to produce the hydrogen, they use solid oxide fuel cell. See that? So then the basic steam coming in, and then the steam is water resources. By the way, solid oxide fuel cell has to operate at 700 degrees C. So at the beginning, when you have water coming in, water actually is the room temperature, is ambient temperature. But the steam really helps. Steam means from the Haber-Bosch plant is really help, because they save the energy. You don't have to heat. You don't have to preheat the water if you have steam coming in. So where do you get steam? Remember yesterday we mentioned Haber-Bosch is isothermic reaction. For isothermic reaction, so you can do the heat changer and then have water come into the reactor and then generate steam. So that's really the heat integration. So you utilize the waste heat from the Haber-Bosch to fuel to the support electrolyzer. Otherwise, you have to spend extra energy to the heat of the water. So anyway, that's why I did a survey at the beginning. If you are chemistry, chemical engineering student, you should understand this circle. Every time you design the process, number one, you have to worry about the energy balance, but material balance. Energy balance means every time when you have the energy you want to recover, you need to recover the energy. So this is a very good way to recover energy. Okay. So anyway, so this is the Haber-Bosch process. They basically shoot in water from the Haber-Bosch side, generate steam to support the solid oxide fuel cell, so that the water from this side doesn't have to be preheated. All right, so let's go to the next one. So I'm going to talk about, I showed this picture yesterday on the left-hand side, Haber-Bosch in 1913. I'm showing you Haber-Bosch, the process today, 111 years later. So what's the differences? So differences is, if you look at in the old days to make it, all they worry about is a reactor. Reactor means how big the reactor you build, and also the machinery in that day. But the modern Haber-Bosch plant is not just a reactor. Remember I showed you, there are a lot of the recycle and the compression and also the separation. That's why you see this plant is not just one single reactor compared to 111 years ago, but now it's more complex. So the modern ammonia plant is integrated. Integrated means they fully integrated with the hydrogen production and utilize the waste heat, and also the user compress. They share a lot of facilities. So let me go back to let me go back to this. So on the left hand side, this is the modern ammonia plant, which is the picture I show you, is fully integrated. That means there are a lot of utilities that share between Haber-Bosch reactor and the ammonia plant. It's when I say fully integrated, it means it's not like from A to Z. It's like going back and forth. So that's so you may be asking me, hey, Dr. Hu, why you show me this picture again and again? Here's the reason I show you the picture. 100 years ago, when they built the Haber plant, they all worry about the high pressure, high temperature engineering. We solved our problem. Today's machinery, you can machine any reactor at any pressure. 5,000 psi, Haber-Bosch 300 bar. You can make a reactor 500 bar, no problem. Okay. So, but in the old days, it's a so-called single pass conversion. Single pass conversion means you flow nitrogen and hydrogen, and you do not do recycle. So in the modern ammonia plant, you have to recycle, because you do not want to waste hydrogen, you do not want to waste the nitrogen. You do recycle, fully integrated. What's the point I try to make? It's very expensive. For 1,000 tons per day production capacity, anybody want to guess how much it's going to cost? I'm talking about capital investment. You can, if you have any knowledge on the on the ammonia plant using coal or the ammonia plant using natural. This basically on the right hand side, this ammonia plant using natural gas. The capital investment is cheaper than coal because coal you have to do coal gasification. But even for the natural gas as a feedstock to make hydrogen and produce ammonia, anybody want to pick a guess how much is it going to cost for 1,000 tons per day?
Maybe 100 million.
100 million?
100 million.
Anybody want to pick another guess? So one student say $100 million to build 1,000 tons per day capacity. Anybody want to pick another guess? Fine. Just give it a try. You can do wild guess. I can tell you it's more than $100 million. It's $1 billion if you build today. 1,000 tons per day ammonia, it takes you $1 billion build. The rule of thumb is that 1,000, I mean, 1,000 tons per day costs $1 billion. You may ask me, oh, what if I build a 2,000 tons per day? Is it going to be $2 billion? No, it's 1.5 billion. So because it's an economy scale, all right? That's why people want to build larger. I'm going to ask you another question. I hope there's some engineering student here. So 1,000 tons per day costs you $1 billion. I already tell you 2,000 tons per day, which is double, it only costs $1.5 billion because of the engineering scale up. What if you build 500 tons per day? Would that cost you $500 million?
No, sir, it will cost more. It will cost more than the 1 billion. That is.
Thank you. So it's not linear, basically. Okay. If you I used to do engineering the design or build the plan. So if you read the literature or open engineering book, here's the rule of thumb. It's basically I'm going to write something. Okay. Have you ever the power? Have you ever heard of the 0.6 power? Have you ever heard of this? Is a terminology in the engineering design, chemical engineering. So if you design a plant, so the capital cost rule of thumb is called the 0.6 power rule. So what does it mean? So basically, if you have capacity 1, it's good. Basic engineering, I will say capacity 1, capital expenses 1. Okay. So basically, if you have a plant capacity 1 and your capital investment is 1, and you have capacity 2, and then the capex 2. Okay, read this number. So let's say capacity 1 means the 2,000 tons per day costs you, X. I would say the X dollars. Okay. And then the cost dollar Y. So basically, this capacity ratio. So you take the ratio. One divided by capacity 2, and then you take that ratio, and then basically and then with the dollar amount, okay, and then build in the. I don't want to go through the good example. You can try dollar amount, and then the dollar X because dollar Y. So how you make a linkage? So basically, it's called 0.6 rule. 0.6 means, so you basically multiply 0.6 the capacity, no, it's not it. You will end up with those dollars. Okay, that's why I don't want to go through detail. There's a formula you can calculate. It's not linear. Linear means it's 1. It's 0.6 means that's how I come up with. So 1,000 tons per day. If you go to the 2,000 tons, it's not going to be 2 billion, from $1 billion to $2 billion. It's a 0.6 rule. Basically 2 divided by 1 times 0.6. So that's the rule of thumb. Okay. So anyway, so so it's a very rough analysis. That's why in the engineering world, the people basically going through all of this. So I think we are almost end with this. I know I'm going very slow, but I promise you, we are going to take a break. When you come back, we are basically going to go through the exercise, and then I'm going to talk about why we do microwave and how the microwave. We don't go through the 1,000 tons per day. We go to the Haber-Bosch. We basically go through the different so-called modular production. Modular production means you do smaller, you multiply. Anyway, so I think Dr. Anand, Dr. Anand is here. Is that right? So should we take a break? I think that there's a break. Is that right? So I will have students go to the 30 minutes break. Come back in 30 minutes. Correct?
Yes, sir.
Yes.
Okay. All right. Thank you, everyone. Yeah.
Thank you, sir.
Yeah. I will see you in half an hour.
Yes.
Yeah, yes. Thank you.